everybody to today's webinar. My name is Dan Combest, and today we'll be talking about vehicle aerodynamics simulations with elements. Some of the goals today, I'd like to introduce some important considerations with vehicle aero simulation. I hope that you'll obtain a sense of how external aero cases can be set up and solved within elements. And then I'd like to accomplish all of this in around 20 minutes, and then finally we'll answer all questions via email post-webinar. So you can just hit reply on the webinar invite. First off, let's talk about the role of aerodynamics in vehicle design. Then we'll talk about some important simulation considerations. Then we'll actually dive into the learn by example, and I'll leave you with a few take-home messages. When we think of aerodynamics and vehicle design, I think the first thing that comes to mind, and probably the number one, is about aero performance. And that directly relates to fuel economy, to emissions, to acceleration, to top speed, but has many other implications and many other areas that we need to think about. For example, we need to think about local forces on the body, on the glass surface, on each one of the components, and how that affects the design of each one of those items. We would need to think about drivability, overall stability or self-steering properties, cooling performance. So how does that air not only move around the vehicle, but how does that air move into the body of the vehicle to cool the engine, to move over the engine? We'll also talk about or think about radiators and brake cooling and condensers. So we need to think about all of these different aspects. Next, we would think about acoustics, internal noise, external noise, deeply tied to aerodynamics of a vehicle. Next, human comfort, heating, ventilation, air conditioning. And then next, visibility and sensing. So external aerodynamics simulation is a key analysis activity. Overall, we're evaluating one of the main sources of energy loss, but also we have to think about it as balance of design, aesthetic, and performance. Aerodynamic simulation is actually a key component that supplements other analysis steps. So some important simulation considerations to think about. I'll break these into two main groups. First one is flow around the vehicle, and then the second group is flow through the vehicle. With flow around the vehicle, one of the most important areas to think about is the front of the vehicle. And I say refinement in front of the vehicle, we need to make sure that our mesh is resolved to accurately capture the pressure gradient along the length of the vehicle. We also need to resolve the flow being diverted into the body for cooling purposes. So if we don't have a well-resolved mesh in the front of the vehicle, we're not going to resolve the air moving through the grill, through the radiator, around the fans, around the engine components in the engine bay, and then our underhood thermal analysis may be off. Next is layer addition and turbulence model. These two kind of go hand in hand. We need them both to accurately predict the boundary layer formation on a body, so how the air moves over the top of the vehicle, around the vehicle, and then how it maybe detaches from the top of the vehicle or even the sides of the vehicle. We need to make sure that we have accurate boundary layers along the top of the vehicle or around many of the different components to predict the behavior of this boundary layer, attachment and detachment. We also need to have good layers around a vehicle or around components to accurately predict the viscous forces within high velocity gradient regions near the surface. If you're familiar with drag, there's two main components. There's pressure drag and viscous drag. So the first area of interest was making sure that we accurately capture the pressure gradient along the length of the vehicle. And then now we need to make sure that we're accurately capturing the viscous forces and viscous dissipation near the vehicle surface itself. Next is accurately resolving the wheels. So we need to make sure that we capture the wheel motion physics. There are different models and different approaches that we can use to capture the actual motion of the wheels. We need to capture the physical geometry of the wheel. So we need a mesher that's capable of resolving all of the tread, any of the complexities inside of the rims, things like that. And then we need a post-processing methodology to be able to capture the contributions to different design variables. And then finally, for flow around the vehicle, one of the most important components is resolving wakes. So we need not only a turbulence model to capture the dissipation behind the vehicle itself, but we also need the time scales, the appropriate time scales to not filter out important physics, and the appropriate mesh resolution to resolve important wake physics. And all of this kind of ties back into viscous components of drag and pressure components of drag. If you have too coarse of a mesh or your time scales are too coarse, then both of those components are going to be way off in the end. Moving to flow through the vehicle body, porous media models for radiators and condensers, fan models to capture additional flow. And a fan model could be an actuator model, it could be an actual fan geometry with an MRF. And then finally, we need the meshing capability to create zones. So this is a condenser and a radiator stacked on top of each other, and then there might be a fan right here. We need the capability to create these zones to apply these source terms to the momentum equation. But we also need the meshing capability to mesh the small features around each one of these vehicle components, maybe do distance refinement, maybe do different surface refinements to accurately capture the geometry within the engine bay. All right, at this point, let me move on to the setup of an example. In today's example, I'll be using a NASCAR geometry. We'll be using the automatic hex-dominant parallel meshing capability within Elements itself, with best practices for stock car external aero. In terms of turbulence, it'll be a transient incompressible flow analysis with delayed detached eddy simulation, specifically using the Spillard-Almaraz model. In terms of velocity, we'll be using a speed that's rather slow for NASCAR, but kind of standard for OEMs, would be 38.89 meters per second at 0 degrees yaw. This will be an open road setup with moving ground and rotating wheels. And when I say rotating wheels, I mean I'm going to be using a rotating wall boundary condition. And then finally, I'll be ignoring thermal effects. So I've already created a new case, and when you create a new case inside of Elements, you're met with this screen. This is the general CFD interface. Now, if we want to use the automatic best practices that are built inside of Elements, we need to go over here to the external aero wizard. And when we start the wizard, we're met with configuration files. These are the default configuration files. They're called the Open Road Elements defaults. One of the neat capabilities about Elements is that we're able to create our own configuration files and make changes to meshing parameters and numerics, how long we're running the simulation, the size of time steps, things like that. So for today, I'm going to select the Open Road defaults. We can break down our best practices in terms of shape of the body. Let's do stock car. And then let me import the geometry. We're importing an STL geometry, and we're not going to do any translating, rotating, scaling. If the geometry was in millimeters originally, I would check this box. And then we're going to convert it to what's called ENGYS binary format, which is a format that ENGYS has created to allow geometries to load faster in the GUI if you were to run this case again. All right, so this was a single STL file, and it had many different child surfaces that represent the different components within the vehicle itself. So right now it's all one surface. So now I need to take this and I need to assign a different assembly type. And what is an assembly type? It assigns different meshing parameters, or it assigns different models. So for example, body, this is something that maybe external aero touches. It has layers, it has a very fine refinement. Wheels, it also touches external air, it has a fine refinement, but when it comes to setting the boundary condition, this will be a rotating wheel geometry, so there's a few extra components we need to set. For porous media, this would set the porous zone that might represent the radiator. And for something like a cockpit or a splitter, these might be specialized for that particular body type. All right, so let me start with the wheels. So I've got different components, and let me select them out and categorize them as wheels. So already you can see that the GUI has sensed the location of each one of these wheels. It's also given me this vector on the front left. This arrow tells me exactly where the center of rotation is for that wheel, and then using the right-hand rule, we can figure out exactly how this wheel is going to be rotating because it's driving in the -x direction. So it's automatically detected that. Calipers. Now these calipers, they're not going to be rotating, so we don't need to categorize them as wheels. They're going to be behind the wheels, and so I'm just going to categorize them as either engine bay or underfloor. Next, let's look at the body. So the body roof, this is a component on top of the vehicle. The body upper external, that's also a body. The windshield, gas cap, if we want to keep that as a body component, we can. Hood panel, sure. Interior. All right, so this is something on the interior of the vehicle where the driver would sit. I'm going to categorize that as cockpit. And then let's go spoiler, rear windshield, side windows, hood panel. All of these are body components, roof fins, body. Because these are fins, I'm going to leave these as type body, and then the underfloor pan, I'm going to leave that as type underfloor. The window nets, categorize those as cockpit. Window trim, I'll leave that as body. And then one thing, if we want to, we can leave this detail. Hood bolts that secure the hood itself, if I want to, I can leave them, or if I feel like it, I can just go ahead and remove those. I think for this case, I'm going to remove them. All right, all these parts have been categorized correctly. Let's go to the wind tunnel. All right, here you can kind of see some of the refinement boxes around the vehicle itself. So here we have a cylinder to resolve the front of the vehicle for the pressure gradient that we're going to see. Let me just hit 5 to move everything to this angle right here, and I'll press P to turn off parallel projection. So we can kind of see the bottom of the wind tunnel needs to be adjusted, so let's automatically adjust the floor height. All right, so we've brought the floor height down correctly to the bottom of the tires. Fantastic. And then we're doing a 0 yaw angle. Move on to the run settings. Test velocity, I'm going to leave it exactly the same. Wheelbase, let's automatically sense this. And then frontal area. If we had laser measurements of the vehicle in the wind tunnel, we might manually go ahead and sense that. If we want to, also we can use this widget to calculate the frontal area. So I'll go ahead and do that. If we wanted to, we could go further and we could adjust the ride height. But for now, I'm going to assume that everything is where it needs to be, and let me just hit apply settings. All right, when you hit apply settings, it actually writes all the surfaces because we did a little bit of surface manipulation by splitting them up into different STLs. It also sets all of our meshing parameters, so let's just choose the wheels. So for the wheels, it's specified a level 8.8, and this is a relative surface refinement. It also assigned a distance refinement for volumetric cells, different distances from the wheels themselves. And then if we want to look at, say, a wake box, the wake box is a volumetric refinement to capture the wakes around the vehicle, or in front of the vehicle, or the side of the vehicle, depending on which one of these wake boxes. It could be the underbody right here. And then if we move to the setup tab, we can see that most of the components are walls. So these little icons mean that most of them are walls, but some of them are just standard no slip walls, whereas others are actually moving walls. So this is a rotating wheel special boundary condition, and if you remember with the vectors that we saw around the wheels themselves, this is the origin and axis of rotation for that. It was able to automatically sense the contact radius, and based on our simulation speed of 38.89, it set the hub speed, and it was able to do that for all the different wheel components in their different locations very nicely. So not only does it set all the boundary conditions, it sets the physics, for example, the turbulence model. It also sets things like the runtime controls. So how long are we going to run this simulation? How often is it going to write? And then we have a strategy for adjusting the time steps throughout the duration of the simulation. And so each one of these are controlled by best practices. Also field manipulation, so we're going to do a little bit of field averaging on different variables of pressure, velocity, pressure coefficient, wall shear stress, things like that. And then we also use field process to generate some data during the simulation process itself. We're We're also going to capture lift drag data on these different components. So how we specified these components also controlled what shows up in these list of patches. And then also we automatically set the initialization method. So at this point, if we were ready to go and we were running on our cluster, then I would hit run all. And during this run all, it would mesh, set up, and launch the solver, and then it would generate a report afterwards. What happens when a result is generated is that you're given a lot of information about lift and drag, but you're also given lots of images about the vehicle. This is just a fraction. So we have different slices of data on velocity and pressure coefficient, total pressure coefficient. We're given streamlines to show the flow around the vehicle. If there was an open engine bay, then we would see flow through the vehicle. We can also see surface values of, say, mean velocity or pressure coefficient, and then we might see the development of drag along the length of the vehicle. So there's lots of little bits of information that are all pulled together in one single report. And within this report, we're given aero case information about when it was run, how many cores, who ran it, how long did that case take. There's extensive volumetric data and images, like I mentioned, for slices, isosurfaces, streamlines, surface plots. All of this is customizable via Python, and further data can be created in situ, meaning while the simulation is running with runtime post-processing. So in the step after I hit apply defaults, I could have gone through and set up additional slices, set up additional data analysis, and use that information to do something like create a video. Maybe I could zoom in and see exactly how the flow might be moving over that rear spoiler, and I would be able to do that and dump out data as it was running the simulation. So a few take-home messages. First off, vehicle aero simulation gives us much more information and plays a greater role than just aero performance. I think that may be obvious to people that are already working in the automotive industry, but for people that are new to this, you have to think a little bit wider than just lift and drag. Simulations can be tedious to manage and tricky to consistently set. Elements is a framework for automotive simulation centered around aerodynamics. Because aerodynamics simulation plays such a key role on a lot of other analysis, Elements is built around that. Also, Elements is built on proven aero best practices. We've worked with our partner company, the Auto Research Center, to develop these best practices. However, they're all still customizable. And then finally, Elements is more than just car aero. So customers use this information, use this data in acoustic simulation. They're also able to use it in heavily automated processes for their analysis. And then it can be coupled to other tools like thermal analytics tools to perform under-hood thermal simulation.